Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And as you know, this is the DADM 3 which is data analysis and decision making 3 course under the NPTEL MOOC series, and this total course duration is 12 weeks, which when converted into number of hours, contact hours is 30 hours in total, and the total number of lectures is 60, which means that each lecture is for half an hour. And after each week, each week being for 5 lectures, we have of half an hour each, we have an assignment, and we have already completed 3 assignments, as you can see from the slide, which is the lecture number 20, which is the 4th week, ending of the 4th week. We will wrap up the 4th week, and obviously we will take the 4th assignment. So, obviously you have already completed 3 assignments, now you will do the 4th assignment, and in total you have basically 12 assignment, and after the 12 assignments of the course ends, you will basically have one of the final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we were discussing about the primal dual problem, which is more of a conceptual basis, that it is a intuitive part where you are trying to basically solve a primal problem. So, primal and dual are words. So, the dual can also be said a primal, and its counterpart would basically be then the dual one. So, if I say the primal one is the dual, then the dual one basically becomes the primal. In the sense, the primary problem and its opposite one, which is just the mirror image what we are going to consider. We consider that maximization becomes the minimization and vice versa, greater than sign and less than sign also comes into the picture. In case if x1, x the vectors are all greater than 0, then they become unrestricted and so on and so forth. And I will come to the conditions with this example, which we are just discussing in the fag end of the last class, which is the 19th lecture. And also we will consider the number of constraints or number of variables which were there in the primal one would just be the counterpart, in the sense number of variables now becomes the number of constraints, and number of constraints now becomes the number of variables. So, if you consider this problem where I was just discussing the primal problem, it was a maximization problem. So, obviously the intuitive dual part would basically minimization problem. So, let me draw it. Draw it means just note down how the relation. So, the maximization problem becomes the minimization problem in the dual problem. Now, if you consider the maximization problem or the primal problem, you basically have, technically you had initially 2 variables x1 and x2, and then later on as we added or subtracted the slack or the surplus, it can be added or subtracted depending on whether it is a greater than sign or less than sign. We basically had S1 and S2, hence the equality sign was there for the constraints. Now, what we will do is that as there are 2 constraints, we will consider for the dual problem the decision variables as y1, y2 corresponding to the 2 constraints which you have, point 1. Point number 2 is that if we consider the total number of such decision variables which are there, in totality for the primal problem there are 4 decision variables, because we will consider x1, we will consider x2, and we will also consider s1 and s2, which are the slacks and the surplus. So, technically now you will basically have 2 decision variables in the dual and 4 constraints. So, let us come check how they are. So, we all know the S1 and S2 are the slack. So, they are greater than 0. If they were surplus, obviously they would be less than 0, but we can convert them with the minus sign to be greater than 0. So, in totality, again I am repeating, you will have x1, x2, s1, s2 as greater than 0. Now, y1 and y2 are the dual variables. So, if you consider the dual variables, they would come here. Now, how the conversion is done? So, if the dual variables are y1, y2, the right hand side of the constraint, which is 8, 8, would basically be the parameters corresponding to the dual variables y1, y2. So, if there were 3 constraints, they would be considered, the right hand side of the equations were 8, 8 and 5, then the dual variables would be y1, y2, y3, and the corresponding objective function in the dual problem would be 8 y1 plus 8 y2 plus 5 y3. So, 5 y3 I just consider, that is why I am saying but in this problem the objective function would now become 8 y 1 plus 8 y 2 as it is written there in the minimization problem, which is the dual problem. Now, let us go back to the constraints. Now, as there are 4 different decision variables, there will be 4 constraints. So, let us first count whether the constraints numbers are right. So, you have the first constraint in the dual problem, the second constraint, the third constraint and the fourth constraint. Now, how are the constraints formulated? So, let us concentrate on the parameters or the variables corresponding to A in the primal problem. So, what are the variables? 2 and 1 for x 1, 1 and 3 for x 2, 1 and 0 for s 1, 0 and 1 for the s 2. So, let us go one by one. So, the first problem which you, and obviously let us, if I go back to the maximization problem, which is the objective function of the primal problem, the parameters are 3 for x 1, 2 for x 2, 0 for s 1 and 0 for s 2. So, let us take all the x's. So, x 1s, so x 1s would basically be the problem which is 2 into y 1 plus 1 into y 2 and there is 3 on the right hand side, but which variable it will be? It will be basically a greater than type depending on the conditions which we have put. So, the first constraint becomes 2 y 1 plus 1 y 2 is greater than 3. The second one would be 1 y 1 plus 3 y 2 is greater than 2. The third constraint would basically be 1 into y 1 plus 0 into y 2, because the parameter value multiplying s 1 for the second constraint is 0. So, it will be 1 y 1 plus 0 into y 2 is greater than equal to 0, because this is 0 here, and the last constraint which is the fourth one for the dual problem would be 0 into y 1 plus 1 into y 2 is greater than 0. So, let us see them one by one. The first one is 2 y 1 plus y 2 is greater than 3, second one is y 1 plus 3 y 2 is greater than 2, third one is basically y 1 plus 0 into y 2 is greater than 0, which is right, and the last one is the fourth constraint in the dual problem would be 0 into y 1 plus 1 into y 2 is greater than 0, and y 1 and y 2 are unrestricted and the values are given accordingly. So, solving the dual problem would give us a value of y 1 as 14 by 10 and y 2 as 1 by 5, which are the dual prices or the worth of the resources in the objective function would be same as it is 128 by 10. If you remember the problem when you have solved, the value was coming out to be 12.8. So, the maximization problem would also lead to the same problem in the minimization problem when you are considering the primal and dual, but the variables which you will have basically y 1 as 14 by 10 and y 2 as 1 by 5 would basically be the dual or the worth of the resources, which would be basically corresponding to the fact of S 1 and S 2, which will come later on when we solve a primal dual problem accordingly. Hence, at optimality, remember that as we approach the mirror, the z, which is the objective function, which is the maximization problem, and w, which is the objective function in the minimization problem, would both merge and the value should exactly be the same as it is 128 by 10 for both the problems. So, let us put the rules for constructing the primal dual problem. So, primal dual are the words, a maximization problem can be the primal one, the dual can be minimization problem, or the primal can be the minimization problem, the dual can be the maximization problem. So, in the primal problem it is maximization problem, the constraints equals to the variables and the variables becomes the constraints as we saw, that means x and y have to basically be differentiated, and the general nomenclature is the primal variables are given by x, the vector x, x1, x2, x3, x4, so on and so forth, while in the dual problem the variables are given by y, y1, y2, y3, y4. Now, remember one thing, I did mention about m and n. So, in the primal problem, if the size of the matrix A is m cross n, that the size of the matrix in the dual problem just reverses, it becomes n cross m, because the number of duals, number of constraints and number of variables are just interchanged numbers, if you remember. So, if the constraints are less than type, they become in the dual problem they become greater than equal to 0. If the constraints are greater than type, they become basically less than equal to 0, and for equality signs for the constraint they become just unrestricted depending on how you have been able to formulate the problems. While in the primal problems, the variables, as I mentioned just few minutes back, becomes the constraint for greater than type. So, if you see, which is very interesting, so this part which you have drawn, this or written, this whole thing which you have written, they are just the mirror image which each other. I will just write it down one by one, use the color brown. So, the variables becomes the constraint here, the variables are for the primal dual. If you see here, if you see the constraint of less than type, they actually become greater than 0, they actually become less than 0. So, these are the same. Now, if they are of the greater than type, it becomes less than 0, greater than type becomes, so greater than type here becomes less than 0 in both the cases, and if it is equality sign, it becomes the unrestricted one. Now, what we are considering in this problem is basically just a simple way of finding a solution for a maximization or the minimization problem in the least effective way, considering that a sparse matrix, because if you consider A is a matrix. So, if the number of rows or the number of columns are very large in any one of the cases, we will be tempted to convert that into a dual problem such that solving that problem becomes very easy from the computational point of view. Now, I will just go to very basic theory and discuss the primal basic feasible solutions and then come back to the primal dual problems again. So, if there is a feasible solution to an LP, then there is a basic feasible solution based on which you can start. So, if you are sure that there are set of feasible solutions, so one of them have to be the basic feasible solution based on which we can start off our iteration process. It does not mention anything about the infeasible solution, I will come to that within few minutes. If the optimal solution where you are trying to get the maximum or the minima exist, then one of the basic feasible solution has to be an optimal one, whether the maximization problem or the minimization problem. So, what you are trying to do is that in very simple words, you will restrict your search algorithm to only the corner points which are basic feasible solution, and one of them have to be optimum if there is a unique solution, or two or more of them can be optimal depending on the number of solutions which you have can be more than one. If you have a basic feasible solution which is not optimal, then provided degeneracy does not occur, degeneracy that means you keep changing the variables of the entering in the existing one, they basically go into a cycle and a loop and the objective function keeps increasing or decreasing in the infinite fashion, arbitrarily large or arbitrarily small depending on objective function you want to maximize or minimize. So, let me read it. If you have a basic feasible solution which is not optimal, then provided degeneracy never occurs, it is possible by changing a single vector in the basis at a time to reach the finite number in time to reach the optimum solution in a finite number of steps, which means the number of corner points can be very large. But if you consider any basic feasible solution, not the infeasible solution, a basic feasible solution, you can keep moving in one direction depending on the maximum and the minimization problem, such that you are bound to reach the optimum basic feasible solution depending on the problem structure which is there. Now, main question is that in which direction you will move, which you have already discussed. So, it means that in the basis in the single vector in the basis at a time to reach a finite number of steps, an optimum basic solution is obtained, or we can show the objective function can be made arbitrarily large depending on if it is an unbounded solution. The next point is that a basic solution exists if and only if the column of equality constraint corresponding to a basic variable forms a basis, that is a largest possible linearly independent collection of vectors are there such that it gives us the basic feasible solution. So, if you have a set of basic feasible solution, it would mean the basic feasible solution as such that the convex combination of this basic feasible solution would lead to the optimum solution based on which you can reach the maximum or the minima. A basic feasible solution, which is the last point, A basic feasible solution of an LP in a standard format are exactly the extreme point solution of the feasible region, as I have mentioned, that trying to basically move along the corner points from the basic feasible solution would definitely lead to the optimum solution, which is also a part and parcel or an element of the basic feasible solution. Now, let us consider the simple problems in a very simple manner. So, consider we have the objective function and we have the constraint also. The constraints are like this: minus x 1 plus x 2 is greater than 0. That means, we have to basically add or subtract a slack and surplus depending on the sign of the equality sign. X 1 is less than 2, x 2 is less than 3, and obviously, x 1 and x 2 are greater than 0 as per the nomenclature of the assumption for linear programming. Adding slack and surplus, we can convert the following constraints into this way. The first equation becomes that as we are, so if it is greater than 0, that means we have to bring down that constraint on the left hand side such that is exactly equal to 0. That means, we will be adding or subtracting the slacks depending on the sign which I am mentioning time and again. So, the constraint basically becomes minus 1 x 1, which was already there, plus 1 x 2 minus x 3, because you are trying to decrease the left hand side of the equation, and we are also adding 0 quantum of x 4 and x 5 depending on the slack and surplus which are there for the second and the third constraint, which we will see that later very simply. So, on the right hand side it is 0. The second constraint, obviously you will basically have 1 into x 1 plus 0 into x 2, because x 2 is not there, obviously it will be multiplied by 0, plus 0 into x 3 or minus 0 into x 3 depending on okay. Now, the question is that whether you plus or minus, that does not matter, is plus 0 into x 3 plus 1 into x 4 depending on the variable which you have, which is basically slack as a surplus for the third constraint and on the second constraint, and the last variable for the second constraint would be x 5 corresponding to the slack or surplus which you will get in the third constraint. So, equality sign on the right hand side is 2. Now, remember one thing, if it is greater than sign, obviously it is minus, if it is less than sign, obviously this is plus. So, when I go to the third constraint, the equation would be there is no x 1, it will be 0 into x 1 plus 1 into x 2, x 2 is already there, plus x 3 is not there, x 3 was basically corresponding to the first constraint, x 4 is corresponding to the second constraint. So, it will be 0 into x 3 plus 0 into x 4 plus 1 into x 5, because this is a less than type. So, it will be added equal to 3 on the right hand in the right hand side. So, now the equation, if you solve the constraints, the overall feasible region is, now I will go slow one by one. The overall feasible region, if you draw x 1 along the x axis, x 2 along the y axis, corresponding to the fact that we are considering a 2-dimensional problem in the initial case, obviously it will change to a multi-dimensional problem depending on how we have been able to add S 1, S 2, S 3, S 4 or x 1, x 2, x 3, S 4, that is the slack and the surplus. So, the constraint regions are, the feasible region is A, B, C and D. If you solve them, you will get it. But very interestingly thing is that the point E and F are basic, but they are infeasible solutions, because the values of the slack and the surplus at the point E and F are negative. I will come to that later on. So, if you consider the overall boundary, right hand side of y axis, which is basically the first and the third and the fourth quadrant, above portion of the x axis, which is basically the first and the second quadrant, and the corresponding region of the other three constraints, one is onto the right left, one is onto the top, one is to the bottom. So, if you consider the overall region, the region feasible region is this. So, what I have hashed, I am trying to basically mark it accordingly. So, I am just marking it, so there is no confusion. So, this is the feasible region and the corner points A, B, D, C or A, B, C, D, if I go clockwise, are the basic feasible region or feasible points, sorry, and the point E and F are basic, but they are infeasible point. I will come to that within 2 minutes. So, now the basic feasible and infeasible regions of the solutions are the corner points which are marked, which is A, B, C, D, E and F. So, when I mark them, the corresponding values which I have, I am marking it very carefully. So, the basic points are, if I consider D, C, E and F, the corresponding values are, for D it is x 1 and x 2 are given, for D it is 0, and x 3, x 4 and x 5 would have basically the characteristics depending on how you have been able to solve the problem. So, if you are considering the corner point which is origin, where you put x 1, x 2 as 0 and solve the problem to find out what is the feasible point, whether it is where is the feasible point or infeasible point, and but it will be basic infeasible feasible region depending on how you have been able to formulate the problem. The point C would basically have x 3 and x 4 as 0 and x 1, x 2 and x 5 would be depending on how the problem has been formulated. The point E would basically have x 3 and x 5 as 0, while x 1, x 2 and x 4 would basically take the points how we have been able to solve. And finally, the point F would have basically x 2 and x 4 as 0, while x 1, x 3 and x 5 would take the points depending on how we have been able to solve the problem accordingly. Now, when I solve them, solving does not mean it is a linear program, you just put this equation, solve the simultaneous equation and get the points. So, solving for the basic feasible and infeasible region, I divide into two color scheme. Blue one are the feasible points, sorry, and red one are the infeasible region. I will mention them, both of them, as basic feasible, basic infeasible. The basic feasible points are like this. D would basically have x 1, x 2, x 3 as 0, 0, 0, and the slack of the surplus corresponding to the second and the third constraint, which is x 4 and x 5, would basically have the values of 2 and 3. Now, pause here 1 minute. 2 and 3 are positive, hence they are basic feasible points from where we can start the search. Let us check at C. For the value of C, x 1, x 2 is 2 and 2 respectively, while the value of x 3, x 4 and x 5 is 0, 0, 1. So, if I consider the slack and the surplus as amongst them is x 3 is 0, x 4 is 0 and x 5 is 1, which means this is also a basic feasible solution based on which I can start the search. From where I start the search, that is a different question. Now, when I consider the point E and F, when I solve them, the values which are coming out for x 1, x 2, x 3, x 4, x 5 for E are respectively like this: 3, 3, 0, minus 1 and 0. So, here I pause. The values of x 1 and x 2 are fine, they are on 3 and 3, which is perfect. But if I look at the values of x 3, x 4 and x 5, x 3 and x 5 are 0, which is also fine, but the value of x 4 is minus 1, hence it is not a basic feasible solution, it is a basic infeasible solution or a basic infeasible point. Now, when I look at the point F, the points are for x 1, x 2, x 3, x 4 and x 5 are respectively as 2, 0, minus 2, 0 and 3. So, if I consider the value of x 1 and x 2, they are 2 and 0, which is perfect, but if I consider the value of x 3, it is minus 2, while x 4 and x 5 are 0 and 3, which is fine, but as x 3 is minus 2, hence it is a basic infeasible solution. Okay, again I am repeating, the values which I got is just simply solve the equation one at a time and then get them, that is all. So, the values which I have for A, B, C, D are, A, B is not given, C, D points are given which are colored blue, hence they are basic feasible solution. If I consider E and F are here, and here if as they are basic infeasible solution, from the diagram also is very clear that the yellow region, which is the feasible region, does not have the point E and F. So, hence starting your algorithm from point E and F is not at all advisable. So, one can immediately understand that as slack and surplus are negative, hence E and F are infeasible, as the case is evident from the feasible region diagram which I shown. The fundamental tenet of simplex method is to move from point to point, which I have already mentioned, depending on some criteria, and in the process improving the search as we move from the corner points and trying to basically maximize, minimize the objective function. We will consider Z as the maximization objective function and W as the minimization objective function. In doing so, the feasibility of the solution of the corner points is also ensured, because if you are moving from feasible region to feasible region, which means that they are the corner points of the feasible set, we are not going into the infeasible region or infeasible points. That is very important to understand. So, consider this problem. We have the simplex problem where you have 12 x 1 plus 9 x 2 and you want to maximize it. The constraints are correspondingly given as x 1 is less than 1000, x 2 is less than 1500, x 1 and x 1 plus x 2 is less than equal to 1750 or 1750, and 4 x 1 plus 2 x 2 is less than equal to 4800, and x 1 and x 2 are greater than 0. So, now here pause 1 minute. So, before I go to the next slide, you are now quite well acquainted that if I add some positive value to the first constraint, that is x 1 plus s 1, it exactly becomes to 1000, point 1. If I add s 2, x 2 plus s 2, then it becomes exactly equal to 1500. If I add a third variable s 3, so x 1 plus x 2 plus s 3 would exactly become to 1750, and if I add a fourth slack of the surplus, depending on how the problem has been considered, but this is a less than sign. So, obviously, you have to basically add the value such that it comes up to the value of 4800. So, the actual equation now would become 4 x 1 plus 2 x 2 plus s 4 is less than equal to 4800. But as you are adding s 1, s 2, s 3, s 4 for constraint 1, constraint 2, constraint 3, constraint 4, the objective function would also change accordingly, such that the objective function would now be 12 x 1 plus 9 x 2 plus 0 s 1 plus 0 s 2 plus 0 s 3 plus 0 s 4 as the maximization problem, while the constraint would now become, now I will show it within 2 minutes, but listen to me carefully, it will be x 1 plus 0 x 2 plus 0 s 1 plus 0 s not 0 s 1 plus 1 s 1 plus 0 s 2 plus 0 s 3 plus 0 s 4 is equal to 1000. Similarly, the next constraint, which is the second one, would become 0 x 1 plus 1 s 2 plus 0 s 1 plus 1 s 2 plus 0 s 3 plus 0 s 4 is equal to 1500. The third one would become 1 x 1 plus 1 x 2 plus 0 s 1 plus 0 s 2 plus 1 s 3 plus 0 s 4 is equal to 1750, and corresponding the last one would become 4 x 1 plus 2 x 2 plus 0 s 1 plus 0 s 2 plus 0 s 3 plus 1 s 4 is equal to 4800, and the last set of variables, which is very intuitive, would be all of these x 1s, x 2, s 1, s 2, s 3, s 4 are all greater than 0. So, let us show it. So, the region is like this, your actual, when I consider the solution, the actual region is like this, your feasible region, if you plot it, so this is the feasible region. Your corner points, which are basic feasible points, are A, B, C, E, F, G. Now, if I consider this point, let me mark it with a not a red color, let me mark with a blue one. This point is a basic infeasible point, this point is also basic infeasible point. So, our search procedures would never start from these two basic infeasible point, they would be any one of the point which is amongst A, B, C, E, F and G, and we will consider that in details in the next class. Have a nice day and thank you very much.